So let's start with drawing out our circuit, which will have 8 arbitrary elements placed in the locations shown. And further, let's have current running through each element equal to these values, where 4 of the values are known, and we are asked to find the other 4, which are unknown: I1, I2, I3, and I4. Now, how do we go about finding these 4 currents to solving this problem? Well, the only way possible is by using KCL at any one of these 5 nodes labeled A through E. And why KCL? Because all the values we are given and all the values we want to find are our current values, and KCL is the only law that relates current values to each other by saying the currents coming into a particular node equal to the ones coming out. Oh, and by the way, if you're wondering why it's 5 nodes instead of 6, it's because these bottom 2 dots don't have any element between them, so we can go ahead and combine them into one node. Now, despite having 5 potential equations produced due to KCL analysis at each of the 5 nodes, labeled A through E for the respective nodes, don't forget that we only have 4 unknowns: I1, I2, I3, and I4. So applying KCL at only 4 of the 5 nodes is enough, since 4 equations is a minimum requirement for 4 unknowns. Think back to algebra, and unknowns require at least n equations to solve. And furthermore, we don't want to select just any 4 nodes, but we want to select the ones that produce the 4 simplest equations, because, why not keep things efficient, right? And the technique for getting the 4 simplest equations is what I've come up with: a simple 2-step process. First, you want to choose the nodes that have the least number of unknowns. Reason behind this is that when you have less unknowns at your nodes, your equation corresponding to those nodes will then have less variables, which means you'll have less algebraic manipulation to do when solving for each individual variable. To better understand this point, consider the following 2 arbitrary systems of 3 equations for the current unknowns Ix, Iy, and Iz that were both produced from KCL analysis at 2 arbitrary nodes. Clearly, the latter system with the fewer variables in each equation can be solved a lot quicker, so we choose a node corresponding to it. Make sense? And second, once you have done that, then out of the nodes you have chosen from step 1, you further select the ones with the least number of branches. This is self-explanatory. More branches means more current values coming in or coming out, so more unnecessary adding. Just compare these 2 arbitrary nodes. You should get the idea. So going back to our problem, let's apply this 2-step technique. If we quickly scan each node, realize that node A has 2 current unknowns associated with it: I1 and I2. The same goes for node C, having I3 and I4, and for node E, having I1 and I3. The only different ones are node B and node D, which only have 1 current unknown associated for each of them: I2 for B and I4 for D. And since these 2 nodes have the least number of variables, being 1, that means we clearly want to include them. So we then decide to eliminate any one of the remaining 3. Now, since these remaining 3 nodes only have 2 current unknowns, we then look for the one with the most branches and then eliminate it. Here, node A has 3 branches, and so does node C, while the different one is node E, which has 4 branches, so we then go ahead and eliminate node E. And now that we have our 4 nodes of choice, let's go ahead and apply KCL so we can then get our 4 equations. Starting with node A, we have I1 and I2 coming in, and 3 milliamps coming out, so equation A is I1 plus I2 equal to 3 milliamps. Next, for node B, we have I2, 4 milliamps, and 9 milliamps, all coming out and nothing coming in. So equation B is 0 equal to I2 plus 4 milliamps plus 9 milliamps. And similarly, looking at node C and then node D, our respective equations for them are as follows. You can pause and go through it. And now that we have our four simplest equations, we can choose one of two routes from here for solving them. We can use basic algebra or we can use linear algebra, meaning we can set these systems of equations into matrices and then we can use Gauss-Jordan elimination to get the identity matrix, and then we pretty much have the answer. We will actually just go ahead and use basic algebra because realize that linear algebra is only necessary the more stuff each equation is. Meaning, if all of our four equations included 3 or even all 4 of the unknowns, then Gauss-Jordan would be smarter, right? But here, realize that 2 of the unknowns are readily given, I2 and I4, since they are the only unknowns in equations B and D. All we do is isolate them completely, and from there, we just plug I2 into equation A and get I1 after isolation, and then I4 into equation C and get I3 after isolation. So we end up getting all 4 of the unknowns in these short 2 to 3 steps, with I1 equaling 60 milliamps, I2 equaling negative 13 milliamps, I3 equaling 1 milliamps, and I4 equaling negative 3 milliamps. In the future, when the equations get messier and require well over 10 steps to solve by using basic algebra, expect me to use Gauss-Jordan elimination instead. Alright? By the way, I know I2 and I4 are negative values, but keep in mind there's no such thing as a negative current. It just means it's going in the opposite direction. If you flip the arrows, then they become positive, but we will leave the negatives. So that should do it. I really hope this video gave you a better understanding of solving circuits using KCL analysis. And with that said, I hope to see you in future videos. Until then, thanks for watching.